of our Department of Marine Geosciences. I just wanted to remind you that eating and drinking is prohibited in this room. And as a speaker, our speaker of today is Itzhak Fouxon. Itzhak is an adjunct professor in Yonsei University of South Korea and visiting researcher at the Hebrew University of Jerusalem. Itzhak completed his master's studies at Weizmann Institute of Science on equilibrium and non-equilibrium fluctuations in fluids, and his PhD also at Weizmann on universal properties of smooth dynamics and their manifestation in physical problems. So Itzhak had 3 postdocs at Weizmann, at Hebrew University, and at Tel Aviv University. And he was awarded by numerous prizes. I will just list several of them, like Daniel Brenner Prize for Outstanding PhD Research, Israeli Knesset Certification of Appreciation for Academic Contribution in 2002, Lady Davis Fellowship for Postdoc, and Alon Fellowship, an award which is granted each year to 10 selected new staff members in Israel. The fields of expertise are turbulence, House, stochastic modeling, non-equilibrium physics, granular materials, turbulence of non-Newtonian fluids, and thermodynamics of black holes and entropy bounds. Please, start.
Thank you again for invitation, and thank you for Revitat for helping. I'm not going to demonstrate lots of slides, much less than you could think of. The reason is that I'm going to tell you something which was derived by theoretical physicists, which I understand that you don't want to listen to it in the form where it was derived. However, these results directly concern what you work on. And I am going to demonstrate this. So we're going to talk of clustering of particles in oceanic turbulence. Why turbulence? Turbulence is the usual state of fluids around us. In this room, the air is turbulent. Each motion we create with our arms creates turbulence. Turbulence is very irregular motion, which we often think of in terms of lots of vortices around us. And thus, even if you work on something very practical, turbulence, which is highly advanced theoretically, has to be dealt with. Often it simply cannot be ignored because it determines lots of things which happen. So I'm going to speak of a certain phenomenon which happens with particles which find themselves in the fluid, which flow is turbulent, and we're going to see that particles cluster. Now, the usual understanding which you have from everyday experience is that turbulence is mixing. You throw a patch of dye in some turbulent fluid, in a while you look at it, you see color is completely uniform. I'm going to tell you that, in fact, this paradigm is not completely true. And where it is not true, it can be very relevant to physical processes. The works which content I will use in this talk, this is the work with Alex Lishansky from Technion, which was published, and recently finished work with Lukas Schmidt, Dominic Krug, Martin van Reewijk, and Markus Holzner from ETH Zurich, which was only recently completed, so it's not published yet. And I'm going to demonstrate you one more slide, which is on the case which was studied and which we did experiment, and it has direct relevance to oceanic studies, as you will see. So when it gets open, for some reason, this time, the file. So this is one of the cases for which what I described holds. you have a situation which is called gravity current. So there is some clear water which is flowing over salt water. So this situation is quite typical in oceans. And what we will see is that particles which are called diffusiophoretic are going to cluster in this situation in these regions. And this was measured with light path. It was predicted theoretically and then measured. In the situation which is quite typical in the oceans, we took particles which are found in the oceans with parameters which are found in the oceans. And we took salinity, which is typical for the oceans, and we found that there is ether. So this is certainly true that this is something which holds in the ocean, that particles are going to cluster. Now I will start describing how this comes about. Could you please raise this? We will start with something which is very simple because it's something which appeals to everyday. So something very simple where this effect was observed first. This is called centrifuge, and you know how it works. So you consider some vortex, some rotation flow. So something rotates. If you put a particle inside this flow, so there is some heavy particle, what will happen with it? If it would be very, very light and easily dragged by the flow, it would start rotating. But it has finite mass, so it cannot completely follow the rotation of the fluid, so it will a little bit deviate from the trajectories of the fluid, somehow like this. So what will happen is that this particle, this is centrifugal acceleration. So the particle will gradually go to the boundary and reach the boundary of this flow. Now, this is how washing machines work. So it's not something which you don't know. That if you take particles because of finite mass, dust particles or some small particles will accumulate on the boundary. Now this sounds very simple. Particles accumulate on the boundary. Now let us consider this thing in the case of turbulence. So I told you that you can think of turbulence as a lot of vortices. And vortices in the simplest consideration are little centrifuges. So if you consider now turbulence, you can think of it in this way, that there is a centrifuge here, centrifuge there, and maybe some other centrifuge here, and something there and there. Now what will happen when you consider particles inside this turbulent flow? Well, if there are lots of centrifuges, well, right, then the particles which are found here will go to the boundary here. The particles here will go to the boundary here, and to the boundary here, and to the boundary here. So the particles will accumulate between the turbulent vortices. Between vortices. Now, however simple this can look, we already got a contradiction. Why? Because of mixing. So what I'm telling you here is that particles are going to accumulate between the vortices. But you know that turbulence is going to mix particles. Particles are going to be spread all over the volume. So how can this come together? Is this clear so far? So somehow this looks contradicts mixing? Well, of course not. We know mixing is experimental fact. By today we know quite well this fact of accumulation of particles as well. So something provides the bridge between mixing and this accumulation in certain preferred regions of the flow. Now, this accumulation in preferred regions of the flow is called preferential concentration. If you hear this term, this is what it is. Now, how do we understand this? And here I'll give you another. So what will happen is this. The distribution, when you look at it, is going to be in practical language, we cannot even tell this if we do not use the word which is fractal. So particles are going to distribute over very rugged structure which is fractal. Now what is fractal? It has zero volume. Now how can this be? So we can now try to understand all this together. So here particles accumulate on the boundary. Here particles accumulate on the boundary between turbulent vortices. Here particles accumulate on fractal with zero volume. Now boundary has zero volume, trivially. Boundary is surface, it has no three-dimensional volume. So boundary between the vortices has zero volume. But turbulent vortices are very complex. They have very complex internal structure. They disappear all the time. New vortices appear. And this happens all the time. So the boundary between the vortices has not to be simple. It is something complex. And this complexity is fractal complexity. Now, what is fractal? For our purposes, it tells you that particles are not distributed uniformly over the volume, but there is certain geometric structure on which they concentrate. Now, would it contradict mixing? No. How come? No. Because if you now look at this thing with finite resolution, you're going to see that this very rapidly smears, so it becomes uniform distribution. Now, what it tells you is that if particles have small inertia, over small resolution scale, fractal distribution looks uniform. Now, this is how clustering of inertial particles works in turbulence. We have theoretical details, have formulas. I will probably write formulas in the last. Do I write it, or it's not going to be helpful at all? I would like to concentrate what you hear on what can be directly applicable. So in this case, what we have, if you think of it, we have the situation where we have rotation flow. There is dramatic difference between particles which have zero inertia and particles which have finite inertia. Particles which have zero inertia, if you distribute the particles uniformly over this vortex, in time they will stay uniform. Nothing will happen. Particles with finite inertia will have completely different situation. You distribute these particles uniformly, but with time they're going to be concentrated completely on the boundary. So we will see that they are here. And this happens however small inertia is. You see that there is something very delicate here. You consider zero inertia, particles stay uniform. You consider very small inertia. And in time, it's not small, the effect is large. So something compensates for smallness of inertia, and this something is time of evolution. So when you now think of turbulent flow, when you consider particles which are passive, that is, they move with the local flow, this inertial correction, you understand that it can be important. It can produce finite effect, and this effect is this clustering of particles on fragments. Now we consider a situation which is of relevance, we think so, to marine snow. So what is marine snow? Well, I'm not the person to tell you, but what is relevant to this in this talk is that there is some agglomeration of particles which causes something that causes precipitation. Precipitation of organic material. It's quite similar with, it has similarity to rain. So when we consider rain, what happens in clouds is that lots of droplets agglomerate, form larger drops, until we have very large drops, which can fall up and from the cloud up until the ground without completely evaporating on the way. This is how rain comes. This is very similar. We have particles which accumulate, and they form larger particles, and then those particles form kind of precipitation, which goes to deep ocean, and there it serves as nutrients for creatures who live there. So it has direct relevance to what you studied. Now, why would this have something to do with this? Well, in fact, until today, I would say that, until what I told you, the opinion is that turbulence is not relevant in the formation of marine snow. What we propose is that probably it can be that it is because of something which was not thought of, and this something is clustering of particles. And what inspires us is that in clouds it is proved by today that clustering of water droplets due to turbulence makes the rain go faster. So it rains faster because of turbulence. So we see no reason why it would not form marine snow faster because of turbulence. The problem was that this way of getting faster collisions of material here doesn't work, because particles which form marine snow, they have very small inertia. So for those particles, this effect is very small. So inertial clustering is small. Other effect is needed for turbulence to be relevant. And this is what we found in this work. What is this other effect? Consider now fluid at rest. So think of ocean. So we don't have to think of some fluid. Think of ocean. And consider inside the ocean, consider colloidal particle. Colloidal particle in the case where salinity is not uniform. And this is often the case, that salinity is not uniform. In fact, more often than not, because there is turbulence, there are lots of disturbances, so salinity not uniform. Now what will happen? This particle, if we have here more salinity and here less, what will happen is that different parts of the surface of the particle will interact with different concentration of salinity. The interactions are electric interactions, chemical interactions, and these interactions will cause different force on the particle from the fluid here than here. So the particle will start drifting, and this drift is called phoresis. In this case, diffusiophoresis. This is the name, which tells you that particles start moving at constant velocity because of local inhomogeneity of salinity. So, inhomogeneous salinity causes motion. Now, what will happen in turbulence? In turbulence, this motion here will be different from here. So here the particle will start moving at some velocity. Now, if you consider in the ocean, the same thing happening here, salinity is a bit different. So this velocity can be, for instance, a bit smaller. So what you will have is distribution of velocity of this phoresis over the ocean, and in the presence of turbulence, this velocity is random and it is compressible. Now, why do I tell you this when I told you this? Because look here. Here we started with rotation flow. Rotation flow is incompressible. What is incompressible? Incompressible tells you that if you start with uniform distribution of particles, it will stay uniform. We included small correction, which is due to inertia. We found clustering. The same here. You consider colloidal particles in the ocean. In the situation where the flow is turbulent, then if you do not think of this phoretic velocity, the distribution of particles will be uniform, because turbulence is typically incompressible of water. Now, if you think of what happens in real ocean, where turbulence is not only there, it causes by itself gradients of salinity. Turbulence produces very inhomogeneous field of concentration of salt. Now, that field will interact with particles, and it will produce small correction of the same type you see here for finite inertia. That small correction produces clustering. So, here, small correction due to inertia gives clustering. Here, very similar. Small correction due to phoresis, which is motion at certain velocity because of local gradients of salinity. Salinity around the particle is not inhomogeneous, so if it's more salty here, the particle will move there. So it will be directed motion. So small correction due to phoresis causes clustering. Now this was proved that this makes rain formation due to agglomeration of water droplets in warm clouds faster. This is quite, you can consider it as factual. There was a lot of work on that, and we know today that it's really relevant. Now here, this makes marine snow formation faster. And here I put this sign because we still do not have measurements. But this is concrete prediction which comes from this work. And it certainly can be tested because we have detailed predictions on how the particles distribute, what will be the increase in the rate. And if you are willing to consider some numbers, you could really see that you could have some crude estimates, whether it will take, say, 10 hours or 1 hour for this marine snow to form because of this effect. So this is something which, if this has some relevance to your work, you can think of. Now, the last thing which I would like to tell you about is phytoplankton, which also has this effect. This effect which I'm telling you is universal. And for phytoplankton, clustering is very relevant. It's called patchiness. And it's relevant because things which feed on small phytoplankton, of course, will go where there is larger concentration of that. Now, what about phytoplankton? In the simple model, which I will consider, I will not write equations. We have a living cell, and that living cell, it behaves in this way. So it can go up in the ocean. Can you see? So the living cell can go in the ocean, can go up to the light, or can go down to the nutrients. So if you think of life of this cell in this simple context which I would like to consider, it goes sometimes to the light for energy, it goes sometimes to the nutrients, in the end also for energy, and it goes for the light during the day, it goes for the nutrients to the deep ocean during the night. And this is what this cell would like to have. It wants to be up in the upper layers of the ocean during the day and in the deep ocean during the night. How does it do it? Well, the particle knows where the gravity is. It does it by displacement of the center of mass. So the particle will somehow, if you think of it, it will know what is the direction of gravity. And using that knowledge, it will start swimming. So it will swim in the direction which is determined by this displacement of center of mass. Now, what turbulence does? Turbulence disorients the cell. In what sense? I'll put here parentheses because it does not only in some sense it disturbs the life of the cell, in the other sense it helps. And here is very question which I'd like you to think of if you'd like to, which is this. So if you consider ocean where there is no turbulence, the cell will move upward or downward. It will know how to do it because it has displaced center of mass and it knows where the gravity is. Now, if the ocean is turbulent, the particle gets disoriented. The flow around it rotates all the time in random directions, and the particle will start moving, will not know where gravity is because there is something which drags it there or there or there. It randomly changes around the particle, and the particle simply loses orientation. Now, is it bad or good? Well, this is a question because, yes, it will destroy this way of going up and down. However, it will also help the particle go up and down because turbulence brings particles very fast to upper layers and lower layers, and it will mix the particles. And whether it will be useful for particle to be inside turbulence or outside is a question. Now, why it could be relevant to marine sciences? It will be relevant because if you now want to know the answer to a very straightforward question, does phytoplankton prefer regions of strong or weak turbulence? I think the answer is not known. But it can be obtained from measurements. So you can really try to correlate the concentration of phytoplankton in the ocean with the strength of turbulence and see what is the preferences. It seems that there has to be a preference because it could be more useful to be in the quiescent ocean where you can go up and down like this, or it could be useful to be in turbulence where turbulence will do the work for you. But what will be less useful is that turbulence will drag you to random direction. So the question is, what will be the result of the net result of this transport of the cell? Now, what I want to tell you is that these particles cluster in the same way as inertial particles, in the same way as diffusiophoretic particles. Why do they cluster? Because in when you consider the behavior of cells, their motion is they have small correction to the local flow because they want to swim in certain direction, in preferred vertical direction. So, living phytoplankton cell does not want simply to be dragged. It tells, well, somewhere there is gravity, there is light, so I'll try to go there. It goes there on the background of this flow, so it will look like there is small correction to the local flow, which is completely of the same type as this or this. So it will bring the same effect of clustering, and this effect received quite a lot of attention recently because this is probably relevant in many contexts. So this brings clustering. Now, I have now some time, more than I thought. So I will now start giving some formulas. I'll try to be, simply tell me stop when it gets beyond the point of understanding. So how do we describe these things? All right, before this, I'd like to do the last qualitative consideration, is that here we know when turbulence is strong so that it disorients the cell, and know when it's not. And regarding this correction and this clustering, this is not observed in dead cells. So this is really, in this case, clustering is what is caused by the fact that the cell is alive. The cell wants to move somewhere. Experiments were done with living cells and dead cells, and it was seen that living cells cluster and dead cells do not. So it's different, really we see that with fluid mechanics, we can describe what happens with living cells. And this is something which quite recent ever, because we didn't have that previously. So now we'll start, it's a good time. We'll start considering how these things are described and what are the parameters which go into this. So we have the flow of the fluid. Now, it will be good if you consider this as introduction to fluid mechanics. right? So I don't think we have to go further because. So how do we describe flow of turbulence? What is the flow? Flow is the situation where you consider different points in space. You have coordinate of the particle in space, and you pose the question, well, the flow which goes at this point is some velocity. How do we describe this velocity? We introduce this vector which tells you this is velocity at this point as function of time. So you see it at the bank of the river. This determines your position, and you watch the flow with the velocity of the flow which goes to that point, and you have some function of time. Okay? This is how we describe flows. Now, how do we describe the correction? So this is turbulent flow. Then we have to describe this finite inertial correction, and it comes like this. So this is So if you consider the particle inside the flow, you can describe it with the law of motion. So you write mass times acceleration is the force. Now what is the force? Force is linear friction. Now I will write this and you tell me if this is beyond what you studied or not. Alright, so what it tells you, what this formula tells you is this. So you consider mass times acceleration is force. What is the force? It's drag. So if the particle is inside the flow drags the particle. How it does it? Linear friction. What is this linear friction? It's determined by the difference of velocity of the particle and the local velocity of the flow. So the flow wants the particle to go with the same velocity as it does. And this is linear friction. What is this tau? Tau is the time scale over which this happens. So there is no reaction of the particle which would be immediate. It takes some time. So if you have some mass, there is some flow which comes. However fast it is, it takes you some time to go with that flow. So this is this time scale. Now, in fact, this time scale, in the way I wrote it, it's we have to multiply it with mass so that it's really time scale. Or we simply consider acceleration times force over the mass, and this equation has this form. Now, how do we find correction due to inertia? Write it in this way. Write it in the way tau dv dt is v minus. Right, there is something. You didn't ask me what is this x of t, so I understand that it's probably. At this point, if you do not ask me what is this x of t, it tells you that you are not really. Alright, so what it tells you is this. You have to take turbulent flow at the position of the particle. And this is what determines the force over the mass. Alright. Okay. I'll stop here. If we have time, we'll continue there. I want you to see how things come here because it's probably a bit simple. So in this context, if you have fluid at rest, then there is phenomenon which is called diffusiophoresis, where you have that particle has velocity v, which is some constant, which is called dp, times gradient of logarithm of c. Alright? So this is very simple formula. C is concentration of salt. dp is constant, which is determined by interactions which are electrical, chemical, of particle surface with salt. So this is some constant which characterizes the interaction. Now this formula is simple, you can understand. So what it tells you is this. You consider the ocean. You consider concentration of salt. You have some field. It depends on where you are. So here, salt, there can be larger concentration than salt. Here, or there, or there. So we characterize inhomogeneity with gradient. Do you know what gradient is? Who doesn't? Because I have to know.
I just want to tell you that here most of the new students, and then we will start studying the gradients and the other similar features in the closest lessons, because they have a course on reduction to mathematics.
So they still don't know.
Some of them, of course, know, and the students in the second year they should know.
Okay.
But the new students they don't.
All right. Then, but they know what is derivative? Usual derivative.
I think so.
Okay. So then it goes like this. So think of the situation where salinity changes only in x direction. So this is something which all of you, which you studied, that if you consider salinity as a function of x, you have some function. This is what you know. Now you can speak of derivative of logarithm of this function. This function is positive because it's concentration. So you take d ln c dx, and you consider multiplying it with certain constant which characterizes the interaction of the particle. That gives the velocity. This is called phoresis. In this case, because we consider homogeneity only in x direction, this is velocity in x direction. Now, consider what happens in the ocean. In the ocean, besides this some profile of salinity, there is flow of turbulence. What will be the velocity of the particle in this case? It will be this velocity which would be without turbulence plus the local velocity of the flow. Taken at the position of the particle. So this is very simple formula. Now this formula, despite its simplicity, is the basis of lots of consequences which can be derived and were derived, because this flow, this is something which I cannot do in one dimension, but because for certain mathematical reason. But what you have, simply think of this, you have the flow which does not cause concentration of particles. It will preserve uniformity of distribution. And you have a correction which can break uniformity. And we can describe how this correction produces this multifractal structure. Now, I want you to understand that this fractality can sound something very, but it's not. It was observed for phytoplankton in experiments, in real experiments in laboratory, that there are fractals over which phytoplankton cells distribute. It was observed that inertial particles distribute over fractals, and it was observed that these particles distribute over fractals. Here we have only started the experiments, but we already see them. Now here some work is still needed, but there is little doubt that this is so. Here it's very solid facts. We have fractal distributions. Now, how do we describe fractal distributions? Now, if you want to understand this, the simplest way to understand is this. So, you think of concentration of particles in space. Now, this is quite similar to this. So here you have some fixed point in space. You see that the velocity at this point of the flow depends on time. Here you can consider concentration of particles at some fixed point in space. It will also depend on time. Now, how do we describe random situations? Turbulence is random. And random tells you that we cannot predict it. So how do we describe the concentration field? We describe it with the quantity, which I think it will be very useful if you learn the definition, even though it could at first look a bit difficult. So I will write it, and then we will see that it's hopefully not that difficult. It's called correlation function. Now, correlation function tells you this. Okay, I see that it will not work. I'll tell you in a different way. So probability, there is always a way to tell some things so that they understood. So probability to have other particle at distance r from given particle is increased due to turbulence. Now, what does it tell you probability if you didn't study probability? This tells you this. So, consider the ocean, consider colloidal particles in the ocean. So, you have something which is, and there are scattered particles. So there is colloidal particle here and here, and for some reason for your research you care where they are because they form physical phenomena which you want to know. So you now can pose the question. They are distributed in some way, so there is some typical distance between the particles. But this distance in turbulence is random. What does it tell you random? It tells you that there is no fixed distance. You consider this particle and this particle, there is some distance here, R1. You consider this particle and this particle, there is other distance, R2, R3, R4, and so on. You have lots of particles, possibly millions, possibly a lot more. So you have lots of distances. And now you can do this. You tell, I don't see a law in how this distance, what is this distance, what is that distance. But simply it's not possible to write this law. But there is something which I can do. I can determine the fraction of particles separated by distance which is between some r and r plus delta r, where delta r, so by distance r, between some r naught and r naught plus delta r, where delta r is much smaller. Oh, you probably don't know this, much smaller than r naught. And this is how theory works. And these things were measured because you consider this experimental apparatus with gravity current, which, okay. So you distribute particles, you let them settle in the flow, and then you really measure distances between the particles, and you determine the fraction of particles separated by this distance. You find how this depends on this R naught, and miracle, it comes what is predicted by the theory. Right? So this is how things work. And this is how it will work in the ocean. We see no reason why not, because in the lab we have really the same parameters which are in the oceans. This is how the things work in this situation. Now, it's a bit different for phytoplankton. And this probably will be the last thing, because this is living cell. The mechanism here is quite different from there, of how this happens. So what happens is this. How do we describe this? We tell that the velocity of the particle, it's very simple. It's very close to this, what we wrote previously, which was erased, that we have velocity of the living cell. which is local velocity of turbulence, plus a small correction, which is speed of swimming times vector p, which is direction of swimming. Vectors were studied?
As usually they study,
Oh.
but not here.
All right, so direction of swimming. So this is unit vector. So unit vector really tells you it's something like this. So this marker has finite fixed length. So if you point it like this, it tells you that the cell moves there. If you point it like this, it tells you that the cell moves there, there, and there. This is this vector. And this phi tells you how fast it moves, because it's not only direction, there are some cells which move faster than other cells. So you have these parameters. Now, this speed of swimming is typically considered constant for given cell. So you consider certain type of phytoplankton in the oceanic application which you study, and you have those particles characterized by certain speed. Now, the particles want to have direction which is vertical, because they, for instance, they could go for light. So they want P to be equal to K. Now K is designation for vector which is upward vector. So if it's this marker, it's like this. So this is what cells want. How do they do this? Well, they have a certain way of interaction with the flow, for which we write equation. I'll write it. So dp dt. I'll write it in the form which will be understandable. So if you have this direction of gravity, this is the upward direction. You have this angle which you learned, or you will learn, that is called polar angle. Then the equation which is written is that time derivative of cosine of theta is minus 1 minus cosine squared theta over psi, or I'll call it tau. So what it tells you is this. Cells want theta equals 0. So the model which is constructed, it's called, it has a name, lots of people study this. It tells you a very simple thing. It tells you this. If theta is not 0, then it tells you that cosine theta is not 0, is not 1. So this is not 0. And it has to be positive, because cosine square is smaller than 1. So cosine will grow, will decrease. Wait. All right, and this writing is like. So cosine will increase until it reaches maximal possible value, which is 1. Okay? So this is how the cells will move themselves. They will change direction of their motion. So how do they know this? If you understand this way of this, what displaced center of gravity tells you, it tells you that you have somewhere gravity which turns you like this. So they use this turn to really direct their motion, and it is described by this model. And the nice thing about this is that if you consider this, and this is the time during which the particle can readjust its motion to the gravity direction, and we can write this correction in the form which is u of t xt plus certain flow, which is, in this case, it's, I will write it down, but it will not be, so this W, for those who know, it's called vorticity, it's curl of the flow of turbulence. You don't have to understand this. What it tells you is that you can write that the particles move with turbulent flow plus a small correction. And this is not different from what we wrote here, when we wrote that V is this plus, in this case for X component of the flow, it's turbulence plus this phoretic velocity. So you see that you have identical description for quite different objects. Okay, so for phytoplankton and diffusiophoretic particles, we have the same framework, which is the flow, which is turbulence plus small correction. And that always brings clustering. Thank you.
Thank you very much, Itzhak. I think that we have time just for very short question, just one question. Yes, please.
Do you check your theory until the moment the clustering begins, or do you continue to watch the current after the clustering to monitor changes that might happen in the current itself because of the clustering of the particles?
I don't like to give some kind of, but this is a really good question. Not because I want to. Now, because it looks like this. So you have fractal, and this fractal is time dependent. So the particles distribute over this structure, which is very rugged structure in space, but that structure by itself, it changes all the time. Now, so how do we deal with this? Its changes are so-called stationary. Now, what is stationary change? It's this, that you consider this distribution of particles, you consider next moment of time, you have a completely different distribution. So the particles are here, there, there, and there, and there, and there. If you look particle by particle, well, this is some distribution, this is another distribution. But if you look at it statistically, these are the same. You find fraction of particles which are separated by given distance, in this case, and you find fraction of particles for completely different distribution, which are separated by this distance, and these are the same. So we call this stationary fractals. So they change in time, but statistically they do not.
Okay, thank you. Okay, thank you for listening. If you should sign the attendance list, please come inside.